So hello everyone, just to introduce myself, I am currently a PhD student at Sorbonne University, so in France, more precisely at the laboratoire Kastler Brussels. So I am in the third year of PhD and I am working with an international collaboration in particle physics dealing with antimatter and normal matter, which is called the GBAR, which aims at testing the weak equivalence principle for antimatter. So we are just doing some simulations with a link with experimentalists to probe the existence of gravitational quantum states and to simulate those such systems. So I will just, as I told you, I am in the GBAR collaboration. So it is an experiment which is led at CERN. It aims at testing the weak equivalence principle for antimatter. It's just simple to understand. We need to have a neutral antiparticle. So we take the antihydrogen, which is the simplest one, antiparticle. We put it in the Earth's gravitational field, and we see if it falls up or down. If it falls down, this means that there is normal gravity. If it falls up, this means that there is anti-gravity. So we have to test it, and such experiment is led at CERN, so in Geneva. And it is implemented, and we are working with experimentalists to do this. We need to use a neutral antiparticle because at this scale, electromagnetism is dominant over gravity. So if we take a charged particle, for example, we will not see the effect of gravity only. So we need to take a neutral antiparticle. I will explain you the design after, but the experiment will be we will have the results nearly about 2 years or after, and we have thought with the designer another original design I will present you after. It uses quantum effects, quantum bounces, to improve the precision of the experiment by using what is called gravitational quantum states. I will detail you just after. So wait a bit. So here is the experimental design. This is the 2D view of the experiment. Normally it's in 3D. It is with a cylindrical symmetry. But here it's just for simplicity, it is a 2D view. So it's in X and Z axis. At the beginning, we have the neutral antihydrogen, which is described in the ground state of it's a Gaussian wave packet with a dispersion zeta in position and dispersion delta V in velocity. It has an initial speed V0. This is due to the because we put the laser at the beginning. This is due to the kick induced by the laser. So this is, and in blue, you can see that there is a mirror. It is considered as a perfect mirror for the reflection. And the anti-atom will bounce on this mirror. This mirror has a length of about 5 centimeters. So you will have quantum bounce. It is, if you want, it's not the image of a classical bounce of a ball, but this is a quantum bounce, meaning that at each bounce, you have a probability of annihilation and bouncing. It is an interaction between the atom and the surface. It is called the Casimir-Polder interaction. So it's a particular force. And due to this force, the atoms will be trapped by the combined action of the Casimir-Polder potential and of gravity. So you'll have this, and you have different possibilities of quantum paths. And after, at the end of the mirror, so here, the different quantum paths will interfere. And you will get at the end an interference figure. And after, you just have the free fall of the antihydrogen atom with a certain height, on a certain height h, a macroscopic height. And you will get also the interference figure at the end. So at the end, the red line that is represented represents the detection plate. characterized, each trajectory is characterized by its position, x, and t, the time of flight. In G-bar, we plan to produce about 1,000 anti-atoms. So we plan to have about 1,000 detection events at the end, each characterized by its position and time. So if we have only the classical free fall, we can do this. It is purely classical. This is a normal design, but with by implementing such quantum effect at the beginning, we will see that this design improves the precision of the experiment. Because at the end, we have an interference figure for the pattern, and this improves the precision of the experiment. That's the design that we want to simulate with Mathematica, with the different quantum trajectories. And as I said, the different quantum paths correspond to different gravitational quantum states. I can also precise that the height of the free fall is about 30 centimeters. And the detection is an horizontal surface. So that's it. Yes. So before going to next slide, I will just share you another figure. So normally you can see it. Here it's another figure representing the bounces on the mirror that is here in blue. So there is only one bounce here, and after the detection at the end on the plate. So you start at the position x0, z0, t0 with the initial speed v0. You have the bounce here at the time tb, and at the end you have the detection with the time big T. So this is the case with one bounce of the detection, but you can also have several bounces on the mirror. Here, for example, you have 3 bounces, each characterized by the time of bounce with a T1, T1, T2, T3, and after the detection time of detection big T. So this is the case with 3 bounds. And I also want to illustrate at the end, we want to produce what intensity is measured at the end. It is like if you want with a double slit experiment for photons, 2 quantum paths will interfere, and at the end, if you want to calculate the intensity, you just sum the 2 wave function and you put a squared, and you have the intensity at the end. This is quite analogous. Here is a figure. You will have, if you want to reach a certain point characterized by the position x, z, and t, you can reach it with a direct trajectories, psi0, or you can reach it by trajectories one bounce. This is characterized by the wave function psi1. So you have those 2 wave functions, 2 trajectories which interfere at the end, and the intensity is given by psi0 minus psi1 squared. Here there is a minus sign, just because during the bounce, there is a phase shift of the wave function of a factor pi. So a factor pi implies a factor exponential I pi. Exponential I pi is -1, and you can find the -1 here. So you just take the 2 wave function, psi1 minus psi0 minus psi1 squared, and you get the intensity at the end. And that is the intensity that we want to plot to see if we can get an interference figure at the end. So the next step is the simulation of the design of the interference between those 2 trajectories. And so wait here. So the code is implemented in Mathematica, of course. So we have different types of trajectories. So, for example, I said, for example, the direct trajectories of the trajectories with 1 bounce, but you can also have 2 bounces, 3 bounces, etc. The classical action. So this is just a semi-classical study, if you want. This is not purely quantum, but this is semi-classical. So the classical action take into account the gravity, the t, the time of flight. This is an expression which is quite famous here. And also first we need to find when you have a certain detection position x and t, z, x, z, and t, we need to find the time of the first bounce, which is noted t1 here, in the reflecting mirror. So this is the code implemented here. You just need to solve a third degree equation. A third for if there is one bounce, or a fourth degree equation if there is two bounce, polynomial equations. So this is the code to solve it. And once we do this, we have the time t1 of the first bounce, and you can also deduce the speed at the bounce also. So I will not enter into detail, but this is the details of the code. Just to solve this polynomial equation, you have the time for the first bounce, and after from this you can get also the speed at the first bounce. So you have this, and after I will just put for the next slide. So the next slide. As I told you, to compute the intensity, we need to sum the different wave function, each corresponding to a precise trajectories with 0, 1, 2, or 3 bounces, etc. And each wave function is given by this term here, exponential I, the action calculated divided by h bar, which is just the normal expression for a wave function. And once we determine the time of bounce, TB, below, we can compute the speed VB at the bounce, and then we can deduce the action by just computing the action for each pass of the bounce, of the trajectories. And the action is given by this term here, SCL, the classical action. So we compute the wave function. At the end, we just sum the different wave function for the bounce we considered. This is this function here implemented in Mathematica. You just also add, as I told you, a phase shift factor, -1 power I. So is the number of bounds you consider. Huh? So it's 0 for the direct trajectories. It could be 1, 2, or 3, etc. You just sum those different terms, and after you can compute the intensity at the end on the detection plate. And now, so this is all the equation we implemented in Mathematica, and I can show you the results. We plotted the intensity on the detection plate. So here it's the current obtained, so the intensity on the detection. So X, the abscissa here is X. This is just, it is in meter. So here is, for example, it is 0.24 meter in average, centered. And you can see that we get a nice interference figure at the end. It is quite analogous if you want with the design with the double slit experiment with photon. Huh? We also get an interference figure here, and you can see here with when we plotted the current. This is the left figure, and on the right, we can also calculate how much bounce is needed. How much bound can we have on the trajectories to reach a certain position? What is the maximal number of bounds to reach a certain position? For example, if I come back to this design figure, for this point here, we can reach it by a direct trajectories or trajectories with 1 bounce, 2 bounds, etc. So for each X position, we computed how much bounce we can have maximum to reach this position. So this is a graph indicated here. Again, with the X in meter in abscissa, and the number of bounds in the y-axis, and you can see that we can reach about 23 bounces and maximum. And you can see that the maximum of the bounces corresponds also to nearly to the maximum of the interference figure here of the current here. That's it. And for big values of x or for low value of x, we don't have any bounces, and this corresponds to the fact that in the interference figure, the current is nearly null, 0. So this is the figure we obtain, but we can also plot it in the 2D view. This is what we obtain. In x, you have, as before, the x-axis in meter. And in the y-axis, you have the t, so the time of flight, because each detection position is characterized by the position and also the time of flight. And you can see that the 2D plot, we have a nice interference figure at the end. So this calculation is just to confirm that with such design, we can obtain at the end an interference figure by because of the interference between the different quantum paths. That's it. And I can also mention that I didn't do it with Mathematica, but I did it with Python. We can compute, for example, the uncertainty of the experiment, the precision of the experiment. And we obtain that with such interference figure on the detection plate, we get a better precision than in the case if there were no interference figure at the end. This is what we can do here. So sorry, the plot here is not on the right, is not really, we have to zoom a bit, but I just implemented the same design as before, but without same design as this one, but without the disk. So there is just the classical freefall. And so I just put d equals 0 here, just the classical freefall, and I want to see what is the consequence on the figure at the end. So normally we should obtain a Gaussian figure because initially you have a certain dispersion, you have a Gaussian wave packet. This wave packet is spreaded during the free fall, and you have also a Gaussian figure at the end. So this is exactly what we obtained. Here on the left, you have a 1D view. You see a Gaussian figure of the current. And on the right, so it's not, we have to zoom a bit, but we also get a Gaussian figure for the X and T axis. So this confirms our intuition. And just to sum up a bit what we simulated such an experiment. If there is only the classical free fall, we get at the end a precision of about, we get at the end a Gaussian figure in the detection plate for the current, for the 1000 ampere atoms that we simulated. But if we put a small mirror just below the initial point, we get at the end an interference figure. And all of this can be simulated with Mathematica with a semi-classical approach. And we also saw that such a design with the quantum passes improves the precision of the experiment by a factor of about 1000 compared to the classical case, which is purely classical, just a classical freefall. I can also mention that such system we want to implement it for the G-bar experiment, so for antimatter, but it can also be generalized. We also collaborate with some researchers, for example, at ETH in Zurich, to implement it for the hydrogen, so for normal matter, hydrogen atoms, and to test if it can be also used for neutral atoms. And again, the goal is just to have a better precision for the source experiment. And for the G-bar experiment, I can mention that this is really useful to test the weak equivalence principle with a high precision, but for antimatter. So thank you for your attention. I hope it was clear. And don't hesitate to ask me if you have any questions.